So moving forward, we're having a video lecture about inequalities. We have seen Chebyshev's inequality, which for probability spaces becomes Markov's inequality. And we have seen for convex functions Jensen's inequality. And to conclude this video lecture, we'll now see Cauchy-Schwarz inequality. And this inequality says the following: if a random variable has finite second moment and another random variable has finite second moment, without assuming anything about the joint distribution of these two random variables, besides the fact that they are both defined on the same probability space, so we don't make any assumption about variance, covariance of these random variables, the product of these two is integrable, meaning the expectation is defined and is finite. It is integrable, and its expectation can be bounded from above by this product here, which is the square root of the second moment of each of these two random variables. Well, how can we prove that? I will prove this assuming, or let's assume, that the expectation of x squared equals the expectation of y squared, and they both equal 1. Okay? I will prove assuming this and leave for you to figure out how to prove the general case using this basic case. And the proof is a somewhat dirty trick, which is we take x and y, take the difference of these two random variables, square them, compute the expectation of that, so it will be the second moment of the difference between x and y, and observe first this is a non-negative random variable, of course. So a non-negative random variable, it always has an expectation, and that expectation is non-negative. On the other hand, we can expand what is this random variable we are computing the expectation of. So this is the expectation of what? Of x squared plus y squared minus 2 times xy. And we see expectation is linear. I mean, this factor here, we know it is integrable, so we can take it out of the expectation. We can always add an integrable factor to an expectation and take it out. So this, we can take this factor out, so this will become expectation of x squared plus expectation of y squared minus 2 times the expectation of xy, if it is defined. But now we see, well, what this is saying, because of this is more than or equal to 0, this being non-negative, it is telling us that 2 times the expectation of xy is bounded from above by 1 plus 1, which is the expectation of x squared and the expectation of y squared. And, well, we can cancel these factors. We have just 1 here, and this 1, well, the 1 is exactly expectation of x squared square root, expectation of y squared square root. And this is what we had to prove, so we can conclude this way. If we have been very careful, we're now concerned about the fact that this may not be well defined, and that is not really nice. But now let's just, so that we feel comfortable with this argument, there are two possibilities. Either this is defined or not defined. If it's not defined, that means that the integral of the negative part of x times y has an infinite mean. But now the problem is if when we add x squared and y squared to this variable, and we're having this new random variable, x squared and y squared, they have to be finite almost everywhere. And why is that? Because otherwise their expectation would not have been finite. And so we can assume they are always finite, because we can change what their values is in a set of measure 0. So we can always, from 2 times xy, we can always add x squared and add y squared. And it turns out these are non-negative numbers. They're so they do not take away from the integral of the positive part of x times y. And for the negative part, if this was infinite, just by adding something which has finite expectation, we don't change the fact that the integral is infinite. And if the negative part of this random variable here, if the negative part was infinite, then its integral would not be defined. But this is not possible because this random variable does not have a negative part. This random variable is non-negative, and non-negative random variables always have an expectation. The expectation is always well-defined. This concludes this rather long video lecture about the basic inequalities involving integrals and expectations.